last time we learned how to differentiate implicitly. And today what we're going to do is we're going to use what we've learned there and learn how to write tangent lines, which we already kind of know how to do, but analyze whether or not we could use the tangent lines as decent approximations of the value of the function. And so that's going to be our primary goal today, is to be able to, number one, differentiate implicitly. So we're going to continue to practice that. But also, we're going to approximate values using tangent lines. So let's kind of get into what we're doing here. So this first problem is just kind of a review of what we did last time. So we'll run through this pretty quickly. We're trying to determine dy dx of this equation up here. So the first step is going to be to differentiate both sides. So we'll differentiate the left-hand side. Derivative of y cubed in terms of x is going to be 3y squared dy dx. And then for that minus xy, that is going to be an instance of the product rule. I want you to be careful here because we are subtracting that product. So it might be helpful to just go ahead and write the subtraction sign and then get ready to write whatever you get for that product rule in parentheses. We will have to distribute that negative to both of the terms that we get from the product rule. Okay, so I'll come back to that because that's kind of the hardest part of the whole thing. And then the derivative of 2 is just 0. Right. So now let's take a closer look at that product rule. We have x times y. So this is just going to be like a direct application of like f prime g plus f g prime, where in this case f is x and g is y. So the derivative of x is just 1. So 1 times y plus x times dy dx. So remember, when we're differentiating implicitly, well, not just implicitly, but when we're differentiating with respect to x, the derivative of x is 1, the derivative of y is dy dx. Okay, so from there, I want to try to isolate the dy dx. So I'll start by distributing this minus sign, make sure both of these are being subtracted here. That is going to be an extremely common error, is just to write the minus kind of out to the front of that product rule, and forget that you have to subtract both of these terms. So really just want to emphasize that so you can avoid that mistake in the future. All right, so now I'll collect my dy dx terms. 3y squared dy dx minus x dy dx. And I'll pull that y out to the right. And hopefully you did enough homework problems to kind of see where this is going. Yeah, we don't want to factor out the dy dx as a GCF, and then we'll divide. So first, factor out that dy dx. And then we'll divide both sides by whatever's left in the parentheses. In this case, 3y squared minus x. So y prime, or dy dx, is going to be y over 3y squared minus x. Now, one way to think about this, just to kind of bring it back to when you originally learned about slope, like probably 7th or 8th grade, like even before Algebra 1. The way that you conceptualize slope was sort of the steepness of the graph, and you thought about it as like a rise over run, right? That's exactly what we're seeing here. This is like the rise and the run. This is the slope of that equation. So if we want to find the slope at any point on this curve, we can now plug in the x and the y to figure out that slope, and we'll have the rise over run. Okay, I just want to emphasize that dy dx is the slope. The derivative is the slope. Okay, so let's take this one step further and come up with the equation of the line that is tangent to this curve where y is 1. So we can see up here where y is 1 is going to be like roughly right here. And so our tangent line is going to be doing something like this. Kind of hard to see. If I zoom in, it's like it almost looks linear there, so it's kind of hard to tell. But that's the equation, or that's the line that we're looking for the equation for. So to come up with that equation, we're going to set it up just like we set up all of our tangent line equations. We're going to need a point. We're going to need the slope. And then we'll plug it into our equation, y minus y1 equals m times x minus x1. Now in this case, they gave us a y, but not an x. So it's a little unusual. Usually we get the x. That's all right. We can use the original equation that we were originally given. Okay, this one up here, maybe I'll write it out to the side here, this y cubed minus xy equals 2, to come up with the coordinate we don't have. So we still need an xy to plug into that slope equation, but you're not, or you may only be given one of the two coordinates. And so to find that other coordinate, we're going to plug in the thing that we have, which is y is 1, into this equation, where we see y, and then solve for x. And then we'll have that x coordinate. So if I plug in 1, I'm going to get 1 minus x is 2. Subtracting 1 from both sides, it's going to give me negative x equals 1. And then we're getting negative 1 here? That's odd. Is this the wrong graph? Uh-oh. Yeah, that's weird. Hold up here. Why? Maybe I typed it in wrong. Let's find out.
Oh, I guess it could be on the other side. But why is 1?
Oh, interesting. Yeah, that's weird. Oh, no, that does make sense. What am I talking about? Let's go back. Yeah, no, that actually works. Let's go back here. Yeah, what am I thinking? Yeah. I'm all backwards here. No, this actually it does make sense with x being negative 1. Let's take a look up here. Yeah. So used to first looking at the x and then determining the y, that's what I was doing mentally. Thinking, oh, something's wrong here. But no, this does work. When y is 1, x is negative 1. So, phew. All right. Crisis averted here. Okay, so yeah, so now we got that x coordinate. It's negative 1. Oh, what is all this? There we go. All right, so we got negative 1 as our x coordinate, and now we can use that to find the slope. So the slope equation is what we found in part A. So we're just going to substitute in our x and our y into that slope. So our slope, our m, is going to be 1 over 3 times 1 squared minus negative 1. So we've got 3 plus 1 is 4. We get 1/4 as our slope. So now we're ready to write the equation of our line here. It's going to be y minus 1 equals 1/4 times x plus 1. And if we look back at our sketch here, we can kind of see that should make sense, right? Our slope does appear to be like up 1 over 4, up 1 over 4 on this graph. Okay, so that's all the old stuff, yeah? Let's take this a little further. All right, C says, find the coordinates of all the points on the curve where the line tangent to the curve is vertical. Now, if I look at this curve, and typically you would not have the graph, but if I'm trying to come up with an answer based on this graph, where is the tangent line vertical? Okay, yeah, it looks like at 3, comma, -1, I guess, would be a good estimate here. So that's kind of what we're assuming the answer is going to be roughly. We're looking for the coordinates where we have a vertical tangent line like this. So we're kind of expecting it to occur right there. But let's see if the calculus agrees with us or not. A little bit of calculus, a little bit of algebra here. Okay, so what is true about the slope of a vertical line? It's undefined, right? Yeah, it's undefined. So if we have an equation for our slope up here, right, what is going to have to be true about this equation in order for it to be undefined? Yeah, the denominator has to be 0. So what we're going to do is we're going to set the denominator equal to 0. All right, so our denominator here is 3y squared minus x equals 0. Okay, and I come up with something kind of weird here. I'm going to add x to both sides and get 3y squared equals x. All right. But where can I go from here? Yeah, this is kind of weird, right? It's like, well, how are we going to solve for either one? I don't think that's terribly obvious, yeah? But hang on, there is a way to handle this. Okay, because we came up with this equation specifically to make the slope undefined, right? So whenever this is true, the slope's going to be undefined. So if x has to be 3y squared in order for the slope to be undefined, then we could go back to the original equation, the y cubed minus xy equals 2, and make a substitution into x. Kind of like solving a system of equations. All right, we could take this 3y squared and stick it right here. Nope, not in the y, sorry, in the x. All right, so yeah, let's go ahead and solve this. We've got y cubed minus 3y squared times y equals 2. Now y squared times y is just y cubed. So we've got 1y cubed minus 3y cubed is going to be negative 2y cubed. Then we could divide both sides by negative 2. And we'll get y cubed is negative 1. And so what's the cube root of negative 1? It's what? Yeah, negative 1. Right? Negative 1 times itself 3 times is negative 1. So y is negative 1. All right, so we know then that the coordinates, or at least the y coordinate, has to be negative 1. And if we look back at the graph, we can see that sure enough, yeah, that y value is negative 1, right? We're expecting the x to be 3 and the y to be negative 1. And so far, so good. That's right. Then we plug in that y back into the original equation. Okay, we know y is negative 1. Or actually, we don't even have to go to the original equation. We could go back to this one. 3 times negative 1 squared minus x is 0. So we get 3 times, or just 3. Yeah, 3 times 1. 3 minus x is 0. So x is 3. And look at that. The calculus and the algebra agreed with the geometry. Isn't that great? It's nice when all those representations agree with each other. Yeah. Any questions so far? All right, we're just getting started here, though. Okay. Part D. I think this is our first problem that's extended past a page. Yeah. Now I don't think I have, but it's possible I did at some point. But I don't think I've ever used this notation yet to indicate the second derivative. But that's what that means. Okay, that is the Leibniz notation for the second derivative. So for the first derivative, the Leibniz notation is dy dx, where the Lagrange notation is y prime. You don't need to know these by name, okay? And for the second derivative, the Leibniz notation looks like d squared y over dx squared, whereas the Lagrange notation is just y with 2 apostrophes. So it's just 2 different ways of saying the same thing. Okay, 2 different mathematicians that lived in different parts of the world came up with 2 different notations. Yeah, and they both kind of stood the test of time. Poor Newton's did not, though. Y with a dot on top of it. Yeah, it's just not as common.
What do you do for the second?
That's a good question. I never use that notation, so I would guess just probably 2 dots, but I don't know for sure.
Which way is it, like up or to the side?
Again, yeah, I don't know. I'd have to look it up. Yeah, maybe when we're done, we can look it up and find out. It seems like that'd be an easy Google. Yeah, ask ChatGPT or something. No, we'll look it up when we're done. Okay, so anyway, we want to find the second derivative at the point on the curve where x is negative 1 and y is 1. So we're kind of going back to this point at negative 1 comma 1 right here. Oh, just erased it all. This point right here. And we want to find the second derivative. Now, let's go back to last unit. If the second derivative is positive, that means that our graph is concave up. If it's negative, it means it's concave down. Now, it's a little hard to tell here just because of the way the graph is kind of, barely going up here. But if you had to guess, just by looking at here, and let me erase these curves here. At that point, right here, does it appear as though it's concave up or concave down? Like, is it more like this or more like this? Okay, so it's hard to tell, right? It almost appears as though, it's concave up until some point which switches over. It looks like there's probably going to be an inflection point somewhere in there. It could be. So we need to find out, yeah? So that's what this is asking. Let's find the second derivative. Okay, so that's what this means. This is the second derivative. At the point on the curve where x is negative 1 and y is 1. Now, I went ahead and typed out these equations so we don't have to keep flipping back and forth on the page. But here is the original equation, and here's the first derivative. Okay, we found that in part A. So now let's find the second derivative. So what we need to do is, and actually I didn't show it on the first problem, but we did on our last lesson, is actually show the d dx on both sides. And I think when I write this, it'll be a little bit more clear why the notation looks like this. I think it's kind of, most people think that's kind of weird that, like, why is the squared on the d on the top and the x on the bottom? Like, why isn't that consistent, right? Well, yeah. Well, you're going to see pretty quickly, yeah, when we write the d dx. So we're going to take the derivative of both sides here with respect to x to get that second derivative. Mm-hmm. Yep. And what does the derivative of the derivative give us? The second derivative, yeah. But take a look at this notation. I just want to just pause a minute and think about the notation here. Do you see how in the numerator here, we've got two d's and one x, right? So there's two d's, I'm sorry, one y. And then on the bottom, we've got two dx's. Anyway, that's why the notation looks like that. Okay, but basically it just means like y double prime. It's the second derivative. Okay, so the second derivative is equal to the derivative of this. Now, what kind of rule are we going to have to use here? Quotient rule. Yeah, quotient rule. So maybe I should write the quotient rule out to the side just as a little reminder here. Okay, let's say we have a quotient with a top and a bottom, and we want to differentiate it. It's going to be top prime bottom minus top bottom prime all over bottom squared. So in this case, the top is y, and the bottom is 3y squared minus x. Okay, so let's get started here. So derivative of the top, that's our dy dx. Okay, times the bottom minus the top times the derivative of the bottom. We're going to have to use a little chain rule on that y, so just keep that in mind. But it shouldn't be too bad. 6y times dy dx minus the derivative of just x is 1. So that's the numerator. And the denominator is 3y squared minus x quantity squared. So what we found here is the second derivative. Notice that the second derivative is in terms of the first derivative. Got a little y prime in there. Okay, sometimes it's easier to write it as just y prime. And so if you want to do that, that's okay. I'm okay with that. Now, the question here is asking for us to evaluate the second derivative when x is negative 1 and y is 1. So we found the second derivative, right? This is the second derivative. But now we want to evaluate it at x equals negative 1 and y equals 1. Okay, so the second derivative evaluated at, what was it, negative 1, 1? Yeah, negative 1, 1. Now, how are we going to evaluate dy dx? Yeah, and actually, we already did that, right? At this specific point. If you go back up here, we found the slope, or we found dy dx at negative 1, 1 already. Yeah, it's the 1/4. Now, if this were like an isolated problem, you'd have to do that separately. But since we already did that, we'll just take advantage of the fact we already know what that's going to be. And so that dy dx is 1/4. So 1/4, and then everything else should be pretty straightforward, just plugging in negative 1, 1. So 3 times 1 squared minus negative 1 all that minus y, which is 1 times 6 times 1 times 1/4 minus 1 all over 3 times 1 squared minus negative 1 quantity squared. Whew, all right. Real shame we can't use a calculator on this one, right? But the numbers aren't that big. They're not too scary. We got 1/4 from part B in this problem. So go back to part B, and we found the equation of the tangent line at this point already. And really the key part of that, the dy dx part of that, is the slope, which is the 1/4. So you're right, normally you'd have to find that kind of separately as part of this problem, but we've already done that. Okay, so let's go to work here. 1/4 times, we got 3 plus 1, so that's 1/4 times 4. I'll just leave that as it is. Minus 1 times something, so I'm not, well, maybe I'll just go ahead and keep the 1 there, times 6 times 1 times 1/4. Okay, 6/4 is what? 3/2. Minus 1 would be 1/2. Right, so 6/4 is 3/2 minus 1. So 1.5 minus 1 is 0.5 over 1/2. Okay, on the bottom, we've got 3 plus 1 is 4. So 4 squared. Okay, so 1/4 of 4. Notice how a lot of times these problems are kind of set up so that they kind of work out at least halfway decent. I know today on our quiz we had like 1.5 squared, and that was probably like the hardest arithmetic we've done all year. Right? So 1/4 times 4 is 1. Minus 1/2 over 16 is going to be 1/2 over 16, which is 1 over 32. Okay, so follow-up question. Is the equation concave up or concave down at that point? The second derivative at that point was positive, so it's concave up. Remember, the second derivative positive? If you're in a positive mood, you're smiling, yeah? You're concave up. If you're in a negative mood, if that second derivative is negative, you're frowning. Concave down. Okay, so we really haven't talked about tangent line approximations yet. Yeah, we're like halfway through the notes here. We haven't even gotten started here. So here's where it all comes together, okay, is we want to use the tangent line that we found in part B. Okay, so let's rewrite that. Y minus 1 equals 1/4 times x plus 1 to estimate the value when x is negative 0.9. Now, you might be wondering, like, why would you do that? Why wouldn't you just like figure out what y is from the original equation? Well, if I go back to that original equation, y cubed minus xy equals 2, imagine plugging in negative 0.9 into x and without a calculator solving for y. Not so easy, okay? First of all, you'd have to factor out a y, or no, it wouldn't even be equal to 0. This would be a pretty challenging equation to solve. Yeah? Probably beyond the scope of this course. So what we can do, though, is approximate what the value would be using the tangent line. Because if I draw this tangent line, and I'll redraw it here to the best of my ability, it's going to look like this. Right? Roughly. And you can kind of see that, hey, like it's pretty close to the curve anyway, right? At least around that point. So if I'm interested in the value of the function at negative 0.9, the tangent line value is not going to be exactly the same, but it'll be pretty darn close. And that's why it's called an approximation. So if we want to approximate the value of y when x is negative 0.9, it's a lot easier to plug in negative 0.9 here and solve for y than it is to plug in, let me write it right next to it, negative 0.9 here and solve for y. Now, I would challenge you to try to solve that algebraically with no calculator. Okay, it's not going to be easy. So but that's okay. That's what these tangent lines are good for. Yeah, they're good for approximations. So y minus 1 equals 1/4 times negative 0.9 plus 1. And this is going to be doable. Okay, negative 0.9 plus 1, or 1 minus 0.9 is 0.1. So we have y minus 1 equals 1/4 times 0.1, so 1/10 of a fourth. So this is where the mixing fractions and decimals gets a little messy. Maybe we just think about it in terms of decimals. We got 0.25. What's a tenth of 0.25? Or what's 0.1 times 0.25? Yeah, it's going to be 0.025, right? You're just going to move that decimal place over 1. You're dividing by 10, essentially. Okay, so y minus 1 is going to equal 0.025. And then if I add 1 to both sides, I get y equals 1.025. Okay, so that's our estimate. Okay, so in other words, when x is negative 0.9, y is approximately 1.025. And you can kind of see on the graph that, yeah, that seems reasonable. Yeah, it's right around where it should be, just right above 1. Okay, but we're not done yet. Because this is going to be the question you're going to see on the AP test. Not exactly what we just saw, but the following question, which is you need to determine whether or not this estimate is an overestimate or an underestimate. In other words, is this value above the curve or below the curve? I want you to think about that. You think it's above? You think the real value is less than this. That's your claim. Not sure anymore. So to make that decision on whether or not this is an overestimate or an underestimate, you need to be thinking about the concavity of the graph. It's too hard to tell on this picture. So instead, let's draw like a very exaggerated concave up graph. Like if I have a concave up section that is a little bit more exaggerated here, and I find a line tangent to that curve anywhere where it's concave up, is that tangent line going to be above the curve or below the curve? Below. So when it's concave up, your estimate will always be an under approximation. In other words, the true value will be greater than what we just approximated. If it's concave down and you're doing a tangent line approximation, notice that the line is going to be above the curve, in which case, as long as it's concave down, the tangent line approximation will be an overestimate. Now in this case, we know that it's concave up because the second derivative was positive. All right, that's what we found up here in part D. We saw it was negative, or we saw it was 1 over 32, which is a positive number. So here's what we're going to write as far as our answer. Okay, it's asking is this an approximation over or under approximation? We're going to say it's an under approximation because the second derivative is positive. In other words, it's concave up. So the true value would probably be something just like slightly above this. And you can throw it in your calculator if you really care to see what it is. But I would imagine it's probably like 1.03 or something like that. Any questions? All right, let's do a few more examples here. Yeah. Okay, so here's a new equation. Let's start by determining the derivative with respect to x. So we're going to do implicit differentiation again. That's not going away. All right, so this would be 3x squared plus, I have to use product rule. So 2x squared, this would be 4xy plus 2x squared dy dx. So that was the product rule from that second term. Minus 4 dy dx equals 0. Yeah? Is it starting to click? It just takes practice. Like literally, it's just like any skill that you'll ever learn. It just takes practice. Yeah? Okay, so now we'll isolate our dy dx by bringing everything else to the right-hand side. So I'm going to have 2x squared dy dx minus 4 dy dx equals negative 3x squared minus 4xy. Factoring out the dy dx, it's going to give me that. And then finally, we want to divide to get that dy dx. All right, so this equation is going to give me the slope anywhere I want it. Part B, determine the equation of the tangent line to the graph at x equals 2. All right, so when x is 2, y, it's kind of hard to tell. It's going to be somewhere around here. It looks like 3, maybe 4. I don't know. Let me zoom in here a little bit. We can see a little bit easier. X equals 2. Yeah, I don't think it's like super obvious, but I'm going to at least estimate that it's at 3, and then we'll see if the math agrees with us. So we want this like almost vertical tangent line. Okay, so to get the tangent line, we need a point, we need a slope. The point is 2 comma something, and we can get that something by plugging in 2 to the original equation. So we have x is 2, so 2 cubed plus 2 times 2 squared, y, minus 4y equals 20. So we have 8 plus 8y minus 4y is 20. I'm going to try to do 2 steps at once here. I'm going to combine my like terms. 8y minus 4y is 4y, but I'm also going to subtract 8 from both sides. So y is 3. And so, yeah, our estimate was right on the money there. Yeah, 2 comma 3. Okay, but I also need the slope. All right, here's the point. It's our x1, y1. And now we're going to get the slope. Okay, which is going to be the value of dy dx when x is 2 and y is 3. So negative 3 times 2 squared minus 4 times 2 times 3 all over 2 times 2 squared minus 4. I'll move this over here, give myself a little bit more space here. Okay, so negative 3 times 4 is going to be negative 12. Minus 8 and 3, 8 times 3, 24. And then over, let's see, what would that be? 8 minus 4 is 4. So it's going to be negative 36 over 4, which is negative 9. So yeah, pretty steep slope there, which is to be expected. All right, so we got our slope. And now we're ready to write our equation here. So we got, let's see, here's the answer to part A. Part B is going to be y minus 3 equals negative 9 times x minus 2. All right, that's just a warm-up. Yeah? Y'all warmed up? Okay. So let's use this line to approximate the value of the function at x equals 1.9. So we're going to take that equation. So y minus 3 equals negative 9 times 1.9 minus 2. 1.9 minus 2 is going to be negative 0.1. Multiply that by 9 is going to give me 0.9. And then if you add 3 to both sides, you're going to get 3.9. And if you look back at that graph, that seems like that could be, if I just scroll up just barely, at 1.9. That seems like that could be right. 3.9. All right. Part D says, given that the second derivative is positive, so I'm not going to make you actually find the second derivative, but we'll just tell you it's positive. Is this approximation an over approximation or an under approximation? It's under. Remember, if the second derivative is positive, that means that the graph on this interval is concave up. So just to exaggerate it a little bit, think of a curve that looks like this. Draw a tangent line, and you'll see that that tangent line will be below the curve. Okay, so this is like the actual function, or the actual value, and these are what we're using for the approximated values. So the estimate of 3.9 is an under approximation because the second derivative is positive. So that's what you'll write, like if I ever ask you to justify your answer on a question like that, like how do you know it's an under or over approximation? Well, it all has to do with the concavity of the curve. Any questions about problem number 2? Yeah. I just think it's funny. It takes like an hour to do 2 problems. Yeah. Oh, it's only going to get better. Yeah. All right, last problem here. Or I guess we got 2 more. Can we knock these out? Do we have time? Yeah, we got 10 minutes. We could do these.
We only have 7 minutes.
Yeah, it's plenty.
I think you should give us homework now.
Yeah, I'm sure you do. All right, solutions to the differential equation. So here we're given dy dx. And we're given the second derivative. So this is like our y prime, this is our y double prime, and we're also given a couple of points on, or we're given 1 point on f of x. So this could be like our x1, y1 here. Okay, part A says, write the equation of the line tangent to the graph at x equals 1. Okay, so we already have the point, 1, comma 2. All right, we got that from right here. And the slope we'll find with the slope equation. We don't have to find dy dx, so I'll spare you the implicit differentiation. Here, we don't even have the original equation, unfortunately. But yeah, we're just going to plug in 1, comma 2 here. So we have 1 times 2 cubed is going to be 8. So our equation is going to be y minus 2 equals 8 times x minus 1. If we're going to use that to approximate the value of the function at 1.1, we're just going to plug in 1.1 into x, solve for y here. So we got 8 times 0.1, should be 0.8. Add 2 to both sides, we get 2.8. All right, part C. If we know that f of x is negative, okay, on this little interval here, we want to know, is the approximation for f of 1.1 greater or less than the value of the function? Okay, if it's greater than, then it's going to be an over approximation. If it's less than, it's going to be an under approximation. So what we need to do is figure out the concavity of the graph. Okay, so our second derivative, our d squared y over dx squared, was y cubed. I think we were given that. Yep, y cubed times 1 plus 3x squared y squared. If I plug in, well, let's see here. Fx is negative. Oh, yeah, so we're going to have to plug in. We don't even have to plug in anything here. Because check this out. It's saying that the function here is negative, right? F of x is y. All right, so that has to be positive. Or negative, sorry, negative. So this number right here, if I cube a negative number, that's going to be negative, right? And then over here I've got 1 plus. Now both of these numbers are squared. So everything in parentheses here has to be what? Positive or negative? Positive. And so we have a negative times a positive. So dy, the second derivative, must be negative. So if the second derivative is negative, this is a situation where the function's concave down. And if it's concave down, our estimate is going to be an overestimate. So that means that the approximation is an over approximation. Okay, so it's going to be greater than. So f, so I'll say 2.8 is an over approximation. For f of 1.1. And that's because the second derivative, or y double prime, is negative. All right. Maybe we'll do number 4 another time. Yeah? Does that sound good? Let me give you your homework. I think that's good enough. I'll make sure number 4 is posted online at some point. All right, so we didn't quite get to this problem in class, but let's go ahead and go over it now. If x plus 2y times dy dx equals 2x minus y, what is the value of the second derivative at the point 3, 0? So the first thing we're going to need to do is to differentiate that equation. So d dx of x plus 2y times dy dx equals d dx of 2x minus y. Okay, so on the left-hand side, we're going to have to use the product rule. Okay, so we have this times this. And so, let's go ahead and execute that. So derivative of the first is going to be, derivative of x is 1, and the derivative of 2y is just 2 times dy dx plus, so this is the, or not plus, sorry, times the derivative of the second. So, oh, I'm sorry, times the second. I'm slipping here. Plus the first times the derivative of the second. Okay, so this whole expression here is the derivative of the left-hand side. It looks like I ended up with an extra parenthesis there. Let's get rid of that. And then the derivative of the right-hand side is going to be 2 minus dy dx. Okay, so we want to find the value of the second derivative, and we can see that second derivative is right here. So we need to isolate that, meaning we're going to bring everything else to the right-hand side. So first I'll subtract this, and then followed by dividing x plus 2y. So first let's subtract that whole thing over. So I'm going to have x plus 2y times second derivative equals 2 minus the first derivative minus this 1 plus 2 dy dx times dy dx. Let's see here. That's it. Okay, so now we need to go ahead and divide. And so the second derivative is going to be 2 minus dy dx minus 1 plus 2 dy dx times dy dx, all that divided by x plus 2y times second derivative. Oh, nope, we don't want that. We just want to divide by x plus 2y. Okay, so here's our second derivative, and now we want to evaluate that at the point 3, 0. So what we're going to do is we're going to plug in 3 into x, 0 into y, but then you might be noticing, hey, we've got a dy dx that we're going to have to plug in too. So we're actually going to have to find the value of dy dx at 3, 0 separately. And so to do that, we're just going to take that first equation, that x plus 2y times dy dx equals 2x minus y, and solve that for dy dx. So the first derivative is 2x minus y over x plus 2y. Now, technically, like this expression, you could just go ahead and substitute in everywhere where you see this dy dx. It's probably not worth it, though. Let's just go ahead and evaluate it at 3, 0. So the first derivative at 3, 0 is going to be 2 times 3 is 6. Here, I'll just write it all out. 2 times 3 minus 0 over 3 plus 2 times 0. So that's going to be 6 divided by 3, so that's going to be 2. So now I can go in and substitute all these values into this second derivative equation. So we want the second derivative at 3, 0. So that's going to be 2 minus 2 minus 1 plus 2 times 2. I guess I missed that other one. Should probably highlight that too. 2 times 2 times another 2 all over 3 plus 2 times 0. Okay, so let's see. We've got 2 minus 2, so that's just going to be 0. And then negative 1 plus 4 is 5. So negative 5 times 2 is negative 10 over 3. And so our answer is A. And that's going to wrap it up for these notes. Sorry we didn't get to this one in class. There is another way that you could solve this. And I'll just throw it out there. I'm not going to work it all the way through. But if you solve this equation, if we start from the beginning and we solve it for dy dx, and we get this expression, kind of like we did before. If we want to find the second derivative, another way we could find that second derivative is just to go ahead and use quotient rule on this. So just keep that in mind, that there is a secondary way how you could find that second derivative. You can do it the way I did it, which is to do implicit differentiation, differentiate both sides. Or alternatively, you could have solved for dy dx initially and then just differentiated that on both sides and used the quotient rule. Either way, you should get the right answer. And that about wraps it up for today's lesson. Y'all have a great day.